Hey, today I wanted to revisit the integral from the first video, the integral from 0 to pi over 2 of 1 over 1 plus tan to the power of mx. I found a new way of thinking about it, which could be cool, so hope you enjoy. First things first, and the main thing we're going to leverage when we're addressing this problem is this identity, which is that for an indefinite integral from 0 to a, if you change the argument of the function you're integrating from x to a minus x, you actually have this equivalence between these two integrals, which, depending on the function you're integrating, might simplify things a lot. In this case, it does. It makes things very manageable. So, let's set about proving it. If we let u equals a minus x, then if we solve for x and put it inside, we'll get a minus u as the argument of the function. Our bounds will have to change, so the x equals 0 bound becomes u equals a, and x equals a becomes u equals 0. And du by dx is equal to minus 1 by just differentiating. And yeah, so this gives us all the ingredients we need to rewrite everything. So the initial thing, so 0 to a, f of x dx, that becomes the integral from a to 0 of minus f of a minus u du. So if see the negative came from the du by dx equals minus 1, the a minus u, we've just substituted that in, and the bounds are the wrong way around. We can use the negative sign to flip the bounds the right way up, and we can see that if we compare the end result with the first, it's the same thing, because u and x, it doesn't matter what letter you use, it'll be the same thing. So we're going to use this for our example today. So let's apply this to our integral. We've got the integral from 0 to pi over 2 of this. If we apply the same form, we're going to get that we can put pi over 2 minus x into the argument, and we'll have the exact same integral. Next, if we use the same identity as we used in the first video to kind of split this apart, this argument apart, then we're going to get tan of pi over 2 minus x being what's shown here. But we know that tan of pi over 2 tends to infinity as y tends to pi over 2. So we're going to have to sort out these infinities in the fraction. So if we want to start manipulating this, let's call tan of pi over 2 a. So then the fraction becomes a minus tan of x divided by 1 plus a tan x. And if we divide through by a and consider that a tends to infinity, 1 over a equals tan of x over a, which is equal to 0. So we can zero out the top and the bottom terms, and we're just left with 1 over tan x. If we return to the original integral, we'll see this, that the integral from 0 to pi over 2 of 1 over 1 plus tan to the power of mx is equal to, well, the same thing, except the tan to the power of mx is a reciprocal in the denominator of the function instead. So it's weird. We can manipulate this in some way. We've got an integral is equal to some manipulated version of the same integral. So if we let tan to the power of mx equals b, then if we take a look at the fraction from before, we've got b over 1 plus b. If we manipulate it like this, so adding 1 and subtracting 1, so splitting this off into just b in the denominator, then it's easier to compare it to before. So we've got 0 to pi over 2 of tan to the power of mx over 1 plus tan to the power of mx is equal to 1 minus, well, the original integral that we're trying to figure out. And now we can easily compare the original integral to what this is. So let's just recap everything we've done so far. We've had our integral, which we're going to call I. We found through an identity that this is equal to this. We've changed the argument from x to pi over 2 minus x, and it's evaluating to the same thing. We expanded out the trig using an identity, so it becomes this. And then after some algebra, we manipulated back into this. If we compare this to the original, we're seeing that we might be able to get the definite integral without evaluating the indefinite, which seems to be the theme of this channel accidentally. So we've got I is equal to the integral from 0 to pi over 2 of 1 minus I, which we can see is going to be quite easy to rearrange. So here's our end result. We've got that I is equal to the integral from 0 to pi over 2 of 1 dx minus I. Through simple rearranging, we see that I is equal to pi over 4. So the exact same result as in the first video. Great.